Yes, you might want to do a screenshot or something, because here, these are the questions that I've answered in both the Monday Avatar from last week. Okay, so those are the 6 listed here, and then last Thursday I did one, and then last Tuesday I did one more, and then last Thursday I did several more. Okay, so you might want to take a screenshot. These are questions that I answered last week, and they're in the playlist for last week. Okay, now for this week, we're going. Okay, today is Tuesday, January. Sorry, not January, November 10th. Okay, and by the way, registration started on Monday, so you should get registration date soon, if not already. Okay, so today's Tuesday, November 10th. We're going to start chapter 7, which is part of the final homework assignment. Now, the final homework assignment covers chapters 7 through 10. It's huge. It's 250 points, right? Okay, so chapters 7 through 10 covers that last homework assignment, and that's going to be due. Okay, so I forgot if it was Friday or Monday. I need to check on that. But okay, but that's the final homework assignment, chapters 7 through 10. All right, I'll double check the due date. Now, remember, the homework that's due this Friday, okay, the homework that's due this Friday, that's chapters 5 and 6. Okay, so chapters 5 and 6, that's going to be due this Friday, November 13th, Friday the 13th. At the end of the day, Friday the 13th, the homework for chapters 5 and 6 will be due. All right, remember that Wednesday is a holiday. So tomorrow is a holiday. It's the Veterans Day holiday. So let's salute our veterans. And also, there'll be no class that day. Okay, that doesn't affect us directly. But if you have a Monday, Wednesday classes, for example, they will not meet tomorrow. If you have Monday, Wednesday, say, or Monday, Wednesday, Friday classes, they'll not meet tomorrow. Okay. Also tomorrow, I do plan on sending out the grades for the chapter 0 homework. So then we'll have the first 2 homework assignments taken care of. Right, and I'll still be grading. I'll be grading throughout the Thanksgiving break as well. All right, any questions thus far before we start the final material from chapter 7 through 10? Of course, the chapter 7 material will not be due this week, but do try to keep up. And then at the end of this session, and for the entirety of next session, we'll cover the homework for chapters 5 and 6. All right, any questions before we go on? Again, you might want to take a screenshot or something of these problems we worked on. Remember, as you'll see with what I send out tomorrow, I do have a preference to problems whose solutions I've covered in these videos, right? So it's nice to know what I've done in these videos. Maybe not all the questions, but maybe a fair number of them. All right. Any questions? Any questions? All right, let's begin chapter 7. Questions in chat? Let's begin. Day 25.
Hi, everyone. Let's start chapter 7 on systems and inequalities, although I'll just briefly discuss inequalities, and they won't really be on your homework. We have another blend here, section 7.1 through 7.3, kind of like in trig, and we're going to deal with solving systems of equations. Now, before, old school, you would solve just a single equation, like 2x equals 6, for one variable or unknown. Here, you're solving for x, and x would be 3. But now, we're going to solve a group or system of equations for 2 or more variables or unknowns, like, for example, a and b. And your solution, by the way, will be a solution set. Technically, up here, your solution set would consist of the number 3. Down here, your solution set may consist of 1 or more ordered pairs. A value for A, comma, a value for B. And order can matter. So before, we would solve a single equation for one variable or unknown. Now, we're going to solve a system of equations where our solution set will consist of ordered pairs, ordered triples, and so forth. Here, our solution in the solution set must satisfy this equation. If you plug in 3 for x, then the left side will equal the right side. Now, a solution to a system or group of equations must satisfy all of the equations in the system. So here, the value for A you get and the value for B you get will have to satisfy both the first equation and the second equation. This ordered pair must satisfy all the equations, must solve all the equations in the system in order to truly be a solution. Now, here, this is a system of linear equations. It's a linear system. And hopefully you remember this from your prior algebra classes. Well, some of the techniques that we use to solve linear systems, we're going to see again in this chapter, when we solve linear and nonlinear systems. In particular, we're going to revisit the substitution method, where we solve for one of these variables in terms of the other, and then plug or sub in, and also the addition or elimination method, where we basically add equals to equals, maybe by multiplying through numbers first. So again, the techniques that we saw for solving linear systems, such as these, we can now extend to nonlinear systems. And I'm going to focus a bit more on those in this chapter. Nonlinear systems have the property that at least one of the equations is nonlinear. So you see something like an x squared or an x cubed, for example, in an equation. Let's start by solving this nonlinear system, and let's use the substitution method. The other method we'll talk about may be more appropriate if we have a whole bunch of like terms in both equations. Here, we have this x cubed term kind of sticking out there. So the substitution method might be better than the elimination method we'll talk about later. So let's solve this nonlinear system. It's a nonlinear system because of this x cubed term in particular. But my answer to a solve a system problem will be a solution set, which will consist of one or more ordered pairs of the form x, comma, y. There could be more than one solution here, more than one ordered pair that will satisfy or solve both equations. In fact, as we'll see, the solution set could be the empty set. In some cases, it's all possible pairs of x and y, or R2. Although that will be rare if you see it at all in our homework examples. However, you will see homework examples where the solution set could be the empty set, where there are no pairs x and y that will solve all the equations in the system. Let's solve this system. And we can use the substitution method. We can solve for one of these variables in terms of the other, and we can do this in either of these two equations. We can, for example, in this step 1, solve the second equation for y in terms of x. You could solve for x in terms of y, but as you might see, if you solve for x in terms of y, we're going to end up with a cubed root. That doesn't seem so appetizing. So in the second equation, let's try to solve for y in terms of x. In the first equation, you could solve for either. It could be easier to solve for y. Okay, let's solve this second equation for y in terms of x. To accomplish that, we can subtract x cubed from both sides. Don't say move, say subtract. And we can add 2 to both sides. This will have the effect of isolating y on the left-hand side. And we end up with basically 2 minus x cubed on the right side. That might be a nicer way of writing that. So again, the second equation here can be rewritten as y equals, see y is all alone on the left side after you do all this, y equals 2 minus x cubed. I'm going to circle this and I'm going to call this star because we're going to use this later on. Notice here, we have a nice functional relationship. We have y as a function of x. That's really, really nice, as we'll see. It's really nice if you can express one variable as a function of the other. So for example, no plus or minus jazz. So here we have y in terms of x. What are we going to do? We got this from the second equation. Why don't we take this expression for y and plug in, substitute for y in the first equation? And you should do this in the other equation. If you try to plug this back into the equation you got this from, equation 2, then you're going to end up with something like 0 equals 0, and that's not going to help you any. So take this expression and substitute into the other equation. From here, we get 3x plus the y here, we're substituting with the result from star, right? Y is 2 minus x cubed. We substitute. To be safe, I put grouping symbols, but that's not so essential if you have a plus sign in front. Now, if there's a minus sign in front of the y, then yeah, I would recommend grouping symbols. After a plus sign, it's not so necessary, but I put them in just to be safe. All of that equals 2. The goal ultimately now is to solve for x. We now want to solve for x. I can remove the parentheses. We can subtract 2 from both sides. We see we have 0 on the right side. That's very convenient. On the left side, we have 3x minus x cubed. So I have this function of x equaling 0. This is a good setup. Generally speaking, if I have 0 isolated on one side, I might be in good shape. So over here, we have 3x minus x cubed. What can we do with the left-hand side? Hint, the 0 on the right side might help. We have a 0 factor property, right? Let's factor that. Now, you might be tempted to divide both sides by x. I'd advise against doing that because you're going to lose x equals 0. And it turns out x equals 0 is going to lead to one or more solutions. So don't divide by x because x could be 0. Let's factor. That's safer. Okay. Actually, before we even factor, you could factor this as is, but some of you might prefer having a positive leading coefficient. So you could add x cubed and subtract 3x from both sides. And some of you might prefer this equation over here. So it's your choice. You can either factor this left side over here, or you can factor this right side over here. This might be more familiar to you. What is the GCF? What can you factor out? You can factor out an x. And what's the other factor? Again, don't divide by x, factor out an x. And the other factor will be x squared minus 3. If you had factored an x up here, the other factor would have been 3 minus x squared. And that would have been fine as well. In either case, we can set this other factor equal to 0. 3 minus x squared or x squared minus 3. They do have the same real zeros anyway. You could also factor this. Remember, x plus root 3 and x minus root 3, that would work. But I think many students would use the 0 factor property right now. So remember, x could be 0 or x squared minus 3 could be 0. X equals 0 or x squared minus 3 equals 0. There's no x term in here, so we could eventually use the square root method. We can isolate the square. Isolate the square here. I can do that by adding 3 to both sides. X squared equals 3. And then remember, x equals what? X can be plus or minus the square root of 3. Please remember the plus or minus. A lot of students forget by now. But if x squared is 3, x can be plus or minus the square root of 3. All right. So we have here real solutions for x. Are we done? Are we done? No, we're not quite done. Because remember, our system involved x and y. And our solutions, if there are any, are going to be in the form of ordered pairs. So for each of these x's, we're going to try to look for a partner y coordinate. We're not done yet. We have to find the corresponding y values. And remember, back here in star, what was great about this? The great thing about this starred guy is that it expressed y as a function of x. We're going to reuse this. It's going to be nice and clean. For each x value, there's going to be exactly one y value associated with it. And we can make a table. So in the left, again, we're back substituting into the star guy. This was my star guy, y equals 2 minus x cubed. We had 3 real values for x. When we plug these values for x into this formula for y, well, what do we get? When x equals 0, we get 2 minus 0 cubed, we get 2. And the corresponding ordered pair would be 0, comma, 2. X coordinate, comma, y coordinate. I'll list these ordered pairs out later because we're going to write the solution set later on. Next, let's go to x equals positive root 3. Plug in. Okay, we have y equals 2 minus the cube of positive root 3. But what is the cube of positive root 3? Well, let me ask you something. If an algebra student were to ask you, what is x cubed? What would you say? X cubed is x times x times x. Well, likewise, the cube of root 3 will be, look over here, the cube of root 3 will be 3 copies of root 3 multiplied together. Root 3 times root 3 times root 3. A pair of these will give me 3, right? Root 3 times root 3 is 3. This root 3 is also there. So basically we get 3 root 3. The cube of root 3 is root 27, or it's 3 root 3. So over here, 2 minus the cube of root 3, that's going to be 2 minus 3 root 3. I'll put this in red. 3 root 3. That goes over here. But remember, the full y coordinate is 2 minus 3 root 3. And this is not negative 1 root 3. Do not combine the 2 and the negative 3. Do not combine these. I'll make this little mark here. Do not combine these. This is not negative 1 root 3. The negative 3 and the root 3 are tied together, but the 2 is a separate term. As for x equals negative root 3, it's going to be similar, except that we're going to have a plus sign in the middle. The y coordinate is 2 plus 3 root 3. So now let's gather our 3 ordered pairs. The first one was 0, comma 2. Let's get the other 2. So the solution set is going to be, I'll shrink this a bit, right? So we have the braces to indicate a solution set. The first ordered pair, not that the order matters among these 3. The order matters inside each ordered pair. Don't switch the 0 and the 2, but you can write these ordered pairs in any order. But the first ordered pair I had listed here was the ordered pair 0, comma 2. That was from the first row. Okay. And then the second ordered pair we got was root 3, comma 2 minus 3 root 3. That's this over here. And then we had negative root 3, comma 2 plus 3 root 3. That's this over here. It looks like our solution set will consist of 3 real solutions written as ordered pairs. Each solution is an ordered pair. Here's our first real solution as an ordered pair. Here's our second real solution as an ordered pair. Here's our third real solution as an ordered pair. All right. Now, as time permits, we can talk about checking our solutions. Now, if you're rushing at the end of the exam, you may not have time to do this, but technically we really should do this, especially for nonlinear systems, checking our solutions. Although I will say that, and this is another benefit of star, if we do have y as a function of x, a check is not as necessary. Things tend to work more cleanly. But if you're unable to write one variable as a function of another, then a check may be more necessary. Okay, but technically, it might be good to check. And sometimes it's more necessary than at other times, all right? But you could check your solutions in the given system, the original system, before you got your dirty hands all over it. All right. As you see, warning, there's a danger in trying to check solutions in a later equivalent system you've written down, because you may have made an error by that point, in which case it would not have been an equivalent system. You may have made a mistake. So you really should check your solutions in the original system, in the original given system that you got before you got your hands all over it. Okay, well, it's easy to check 0, 2. Right? It may be harder to check the others, but 0, 2 is a quick check. Okay, so here's our original system. Plug in x equals 0, y equals 2 in both equations. We see here, we get 2 equals 2. This first equation boils down to 2 equals 2. This second equation boils down to 0 equals 0. So the solution 0, 2 checks out. It turns out the other two will check out as well, but it may take more time. Okay, next up, what are the graphical implications of all this? The graphical method. What do these solutions really correspond to? I'll give you a hint. It corresponds to something involving the graphs of these two equations. If you graph these two equations, and take a look and guess what you'd get, by the way, but if you graph these two equations, what 3 points do you think these would correspond to? That's next time.
Okay, so we're going to look at the graphical. Okay, so questions. We're going to look at a graphical approach next. Questions. Okay.
Hi, everyone. In the last video, we solved this system, and we got these 3 ordered pairs forming our solution set. Now, if we think of these ordered pairs as their corresponding points in the xy plane, the Cartesian plane, what do these points have to do with these two equations? In particular, the graphs of these two equations. Well, remember the basic principle of graphing. The graph of an equation consists of all points whose coordinates do what? Satisfy or solve the equation. Whose coordinates satisfy or solve the equation. The graph of an equation consists of all points whose coordinates satisfy or solve the equation. That's true in Cartesian coordinates, polar coordinates, 3D coordinates. That's a powerful concept, the basic principle of graphing. So the graph of 3x plus y equals 2 consists of all points whose coordinates satisfy or solve this equation. The graph of this second equation consists of all points whose coordinates satisfy the second equation. How do you graph these, by the way? How do you graph 3x plus y equals 2? I'll give you a hint. Put this in slope-intercept form. Subtract 3x from both sides. Y equals negative 3x plus 2. What is that? The graph of this is going to be a line, which you can graph either by using the slope-intercept form or by finding the two intercepts, right? The x-intercept and the y-intercept, and you can graph the line. Let's have Desmos do it. Desmos, let's graph 3x plus y equals 2. So again, either by using the intercepts at 2/3, 0. Notice that solves this, 2/3, 0. And also, hey, 0, 2, sound familiar? 0, 2, that's another intercept for this line. It's the y-intercept, okay? Based on these two intercepts, we can graph the line. Or you can use the slope-intercept form, right? That was y equals negative 3x plus 2. It's the same line, right? We use the fact that the y-intercept, again, is at 0, 2, because b is 2, and the slope is negative 3. If you run 1, you go down 3. But either way, we can get the graph of this equation. It's a line sloping downward, and whose y-intercept is at 0, 2. Remember him. Now, what about the graph of the second equation? Well, remember, we already solved that for y in terms of x. That was star. Remember the star relationship here, right? It was y equals 2 minus x cubed, because we like to have y as a function of x. Y equals 2 minus x cubed. Let's rewrite this as y equals 2 minus x cubed. Y equals 2 minus x cubed. All right, over here, let's keep this a secret. Y equals 2 minus x cubed. All right, so let's try to figure this out. What does this graph look like? First of all, what does the graph of y equals x cubed look like? What does the graph of y equals x cubed look like? That's going to be a rising snake going through the origin, right? It's odd. What if we have y equals the opposite of x cubed? What happens if I put a minus sign in front? Flips it. What happens if I add 2 to the right-hand side? What's going to happen? Raises this by 2 units. And look at this. Instead of going through the origin, this point now goes through, hey, 0, 2. This is an intersection point between the two graphs. So if you remembered your graphing from chapters 0 and 1, you should be able to figure out that 0, 2 is a common point. It's an intersection point, and therefore it's going to be one of the 3 solutions we have here. Oh, and how do we know we have 3 solutions? Let's zoom out. If you do a decent job of graphing, you should be able to see that we're going to get 3 intersection points. In addition to the intersection point at 0, 2, we're going to get another intersection point somewhere in quadrant 2. That's a decimal approximation. Now, I realize that you may have a hard time figuring out that quadrant 2 solution is going to have these coordinates. I doubt any human being could look at this point and go, oh, well, this is negative root 3, comma 2 minus 3 root 3, or is it 2 plus 3 root 3? I don't think any human being can go, oh, this is going to be 2 plus 3 root 3. Although actually, you know, negative root 3, I think some students will recognize this as being close to negative root 3. So some observant math students might observe that this is about negative root 3. So I can give you the negative root 3, but the 2 plus 3 root 3, can any human being look at this and go, oh, hey, 2 plus 3 root 3? No. And by the way, you might only get the negative root 3 because you see this number here. If I just said, hey, look at this point here, right, without the corresponding coordinates, you just know it's some point in quadrant 2. You can try to estimate it, but not to this level of accuracy. Likewise, it appears that we're also going to get an intersection point in quadrant 4. And it turns out to be this point over here, this quadrant 4 point over here. But again, I can't imagine any human being just looking at this and going, oh, that's going to be root 3, comma 2 negative 3 root 3. I can't imagine any human being identifying that point. Desmos can approximate it. Notice that's about positive root 3 there. And if you do a decent job graphing, then you might even be able to estimate the coordinates. But 0, 2, you should have right on, 0, 2. And at the very least, you should know that you get 2 additional intersection points, one in quadrant 2 and one in quadrant 4. But in order to find their exact coordinates, then of course, it helped to solve the system algebraically, mechanically. Now let's review this graphical method. Oh, and by the way, as a check, this is a check to see that there are in fact 3 real solutions. There are 3 intersection points. Okay, the graphical method. So the graphical method, which you may remember from your old algebra class, this method for solving a system of equations requires that we graph all the equations and then find the resulting intersection points. This is the key principle. There is a relationship between the real solutions of a system and the intersection points between the corresponding graphs. These points correspond to the real solutions of the system. We're not dealing with I, but we're going to keep it real in this chapter. In fact, we're basically going to keep it real throughout the final material. Now, books neglect to mention that this method is highly unreliable because back in your algebra class, your book was used to giving you systems with integer coordinates in solutions. Now here, yes, 0, 2, that's one that we can pick up exactly very nicely. But your old school algebra books we're less likely to get solutions like these because they were too clean. See, I'm being more mean to you. I might give you a system where you get kind of weird looking coordinates like those, right? That's not fair. All right. So you can't just assume that the coordinates will always be integer. Here they are, but for these guys, they won't be integer or even rational. Okay. And in fact, even if you eyeball something, even 0, 2, some students might ask, why can't it be something like this? So although many textbook problems are designed to have nice solutions, we can't always assume that our solutions will only consist of integer coordinates. It's quite possible that your solutions might be uglier, like irrational. And sometimes when you graph, maybe 0, 2 isn't the solution. Maybe it's just a nearby point like that. Although, if you really think about it, in our example, you should be able to figure out it's exactly 0, 2. Right. So again, I had an old version of Mathematica sketch graphs for these two equations. And like I said, even with a decent graph, you should be able to figure out that there are 3 intersection points. One is at 0, 2. You should be able to get that one exactly. You have one other solution in quadrant 2 and one other solution in quadrant 4. So 3 real solutions corresponding to 3 ordered pairs. In terms of getting the exact coordinates for these guys, you better work out the mechanics, as we did before. Now, in general, I wouldn't recommend the graphing solution as an overall approach, because again, how in the world are you going to pick up a solution like that and a solution like that? Granted, you could pick up this solution, but how are you going to pick up these two solutions? So I wouldn't recommend the graphing approach in general. However, there are some cases where it can really help, aside from just picking up a point like that. Okay, let's consider this example. And if you do a decent job of graphing, so be reasonably careful, reasonably accurate, then you should be able to figure this one out, just graphically. Find all real solutions of the system, 1/2 y equals 1/2 x plus 1, and x squared plus y squared equals 1. First of all, a lesson. A legal move, a legal operation that you can perform on a single equation, you can perform to that equation even if it's in the context of a system. So look over here. 1/2 y equals 1/2 x plus 1. What are you just dying to do to both sides of that equation? Why don't we multiply both sides by 2? I'll do this in blue. Let's multiply both sides by 2, because I know you're itching to get rid of that fraction. Okay, we can do that. Remember, the 2 distributes through, right? So then when we do that, okay, we then get y equals x plus 2. Don't forget the 1 here becomes a 2 here, because we're multiplying, we're distributing in the 2. Again, I'm making the point that operations that are fair for a single equation are also fair for a single equation in a system. Now, let's consider graphing these. How do you graph y equals x plus 2? How do you graph y equals x plus 2? Well, it's going to be a line. Slope 1, y-intercept at 0, 2. Once again. But now, how do you graph x squared plus y squared equals 1? Do you remember section 0.13? That is going to be a circle, the classic unit circle centered at the origin. Okay. Now, if you point to your screen, maybe you can even draw it on your screen. Draw for me that unit circle. Don't be too sloppy. Don't be too sloppy. X squared plus y squared equals 1. Let's make it a different color. Yeah. How about purple? All right. So if you do a decent job of graphing this circle, don't go nuts and make it too ovally. Don't make it an ellipse, all right? If you do a decent job of graphing this circle, how many intersection points do we have between this circle and this line? None. If you do a decent job graphing these things, the answer is none. So therefore, what's the solution set? For the first time, we see that the solution set will be the empty set. There are no real solutions. There will be no pair of real values, x comma y, that will satisfy or solve the first equation and satisfy or solve the second equation. Not going to happen. Empty set. There are no real solutions to the system. The solution set is the empty or null set. Now you might ask, well, let's say I don't trust my graphing. I don't blame you. You've seen my circles. You've seen my circles. So how do you do this mechanically? Well, look at this. This is really set up for the substitution method. I already have y set up in terms of x. Let's substitute into the other equation. But now you're going to have to work out the square of x plus 2. And take a minute, folks. When you perform the substitution, you put x plus 2 in for y. What is the square of x plus 2? I'll give you a moment to remember this. This is chapter 0 review. Let's work it. We have y already expressed as a function of x. Let's substitute this in. And we get, okay, x squared plus, what's the square of x plus 2? It's x squared plus, please do not forget this. I'm going to put this in red. A lot of students forget this. Don't forget to take twice the product of the two terms, the 2ab term. Okay, remember that square of a plus b. Remember that meme I showed you with the teacher, the mad teacher? The square of a plus b is a squared plus what? 2ab plus b squared. Don't miss the middle. Don't miss the middle. Twice the product of the two terms. 2 times x times 2. 2 times x times 2 is 4x. You need the 4x. I don't mind taking forever to push the 4x because so many students forget it on the homework. I see that. Okay, don't miss that middle term. Plus, the square of 2 is 4. People get that. Equals 1. What's x squared plus x squared? It's 2x squared. Now, this has an x squared term and an x term in it. I'm going to want to isolate 0 on the right. Whether I'm preparing myself for factoring or the QF, the quadratic formula, I want to isolate 0 on the left. Subtract 1 from both sides.
0 on the
2x
right.
squared plus 4x plus 3 equals 0. If you try to factor this old school, you're out of luck. There are no rational zeros to this left-hand side. There are no rational solutions to this equation. So let's try the quadratic formula, all right? And what happens when we try the quadratic formula? Well, right off the bat, you might have wanted to work out the discriminant, b squared minus 4ac. This is the discriminant. That's the discriminant, b squared minus 4ac. I'll put the square here. If you work out b squared minus 4ac for that left-hand side, a is 2, b is 4, c is 3. The discriminant, b squared minus 4ac, I'll put this in blue. The discriminant, b squared minus 4ac, turns out to be negative 8. So even without plugging into the other parts of the quadratic formula, if you have a negative discriminant, then you're dead as far as real solutions go, because you're going to have an I involved in there, inevitably. So just by taking this and finding the discriminant, once you find that this discriminant, b squared minus 4ac, once you find the radicand there is negative, you realize game over. What's the solution set? It's going to be empty. Because you can't even find real solutions for just x alone, let alone an ordered pair. You need real solutions for x if you're going to have real solutions as ordered pairs. Solution set is the empty set. You're dead right here. There are no viable real values for x, so the system has no real solutions, and the solution set is the empty set. And this confirms our findings from method 1. There are no intersection points between the circle and the line. Ugh, horrible. All right, again, once you find the discriminant's negative, you know there are no solutions. All right. And by the way, a system with no real solutions, if the solution set is empty, that's often called an inconsistent system in the sense that the two equations are not reconcilable. Actually, the original system was up here. Okay, but we say that the system is inconsistent because it has no real solutions. There is no ordered pair solution, x comma y, that would be consistent as a solution to both the equations. Inconsistent. They don't go together to give us a solution. All right, next up, we're going to discuss the addition or elimination method. Next time.
Okay, any questions thus far about the substitution method and about the graphical approach? Although I don't recommend it as a general solid technique. It's more of a check, perhaps. Any questions? Any questions? It's a good review, too. Ooh.
Hi, everyone. What's an alternative to the substitution method for solving systems? We could try the old addition or elimination method. It's the idea of adding equals to equals. In a way, adding equations. Adding equals to equals. And when can this technique apply well? Basically, if you have like terms, like notice here in this system, we have a pair of x terms over here, a pair of y squared terms over here, and a couple of nice friendly constants over here. So when you have a bunch of like terms, then the addition or elimination method might be a good method. Now, substitution might work also, but here the substitution method would get messy because if you try to solve, for example, for x in terms of y, then you're going to get kind of ugly fractions and students try to avoid those. It's not wrong, and you can use the substitution method, but students might not like the fractions that they get. And if you try to solve for y, well, instead of solving for y, you might solve for y squared instead. And even then, you're going to get some complicated fractions involved. So although the substitution method would work if you solve for either x or y squared, because you get fractions, kind of ugly fractions as a result, maybe it's not so hot. And because we have these like terms here, the addition or elimination method might work better. Now again, the idea behind this method is that you're adding equals to equals. And beforehand, you're allowed to do something. You're allowed to multiply through equations by real numbers, non-zero real numbers. Remember that if you have an equation, it is legal to multiply both sides by any real number except 0. If you multiply both sides by 0, you destroy the equation. Okay, now the addition method, in general, it may not be as helpful in nonlinear systems, but this is a system where we have some nice like terms here. The problem with nonlinear systems is that you often have a term here, another type of term there, another type of term there, and it may not be as nice. But this one, this is a case where the addition method works pretty well. Okay, so now we have the option of either eliminating the x terms right now or the y squared terms. For right now, let's eliminate the y squared terms and then solve for x. Just psychologically, it seems nicer to think, oh, we can eliminate the y squared terms. Wouldn't that be nice? At least for now. So remember, before we add the equations in a sense, we're allowed to multiply through the first equation by a non-zero real number and or the second equation by a non-zero real number. Now, what is our aim? Well, we would like to multiply one or both equations through by non-zero numbers in such a way that the coefficients on y squared, if you want to eliminate the y squared terms, right? Here we're going to eliminate the y squared terms, although you could eliminate the x terms also, but let's eliminate the y squared terms here. Look at these coefficients, positive 5 and positive 2. Wouldn't it be great if we could multiply through these equations by non-zero numbers in such a way that these two coefficients are opposites. And therefore, these two terms with the y squareds are opposites. Because then, when you add the equations, these cancel out. What do I mean by adding equations? The idea is that if we add equals to equals, we get equals. So let's say we have a solution, x comma y. That works for both, okay? Well, what other equation would be legitimate? Imagine a balanced scale. Imagine a balanced scale. Let's see. And let's say that in both the scales, you put a rock with the same mass. Rocks with the same mass. All right. Basically the same weight. Let's say the same weight. Rocks with the same weight. And on top of those, we add feathers that have the same weight. The idea is that if you add equals to equals, you get equals. If these are equal weights and these are equal weights, then the scales should still balance out. When you add equals to equals, you get equals. So if the first equation holds for a given x comma y, and the second equation holds for a given x comma y, then when you add the left-hand sides and the right-hand sides, the resulting equation will be an equation that has x comma y as a solution. All right, so what numbers can we use to multiply through on the top and the bottom to make these opposites? Well, what coefficients might we aim for? Instead of a positive 5, why don't we aim for a positive 10? Let's aim for a positive 10. And over here, instead of a positive 2, let's aim for, well, okay, let's aim for what? How about a negative 10? So I'd like to make this coefficient a positive 10. I'd like this to make this coefficient a negative 10, so that we get cancellations when we add equals to equals. All right, well, 5 times what gives me 10? 5 times 2 equals 10. And 2 times what will give me negative 10? 2 times what will give me negative 10? 2 times negative 5 will give me negative 10. So for the first equation, I want to multiply both sides by 2. Multiply through by 2. I'll put blue here. I'm going to multiply the first equation through by 2. And I'm going to multiply the second equation through by negative 5. So that these coefficients are opposites, and therefore these terms are opposites. Let's do that. We multiply through the first equation by 2. We multiply through the second equation by negative 5. Okay, so we multiply both sides of the top equation by 2. We get 4x plus 10y squared equals 70. On the final, on a final exam, I would allow a calculator, by the way. If you multiply both sides by negative 5, 7x times negative 5 is negative 35x. 2y squared times negative 5 is negative 10y squared. And 14 times negative 5 is negative 70. Now, we wanted these two to be opposites. We made it so. It turns out these are opposites, but that's more luck. What happened here was more luck. We were lucky. These didn't have to be opposites over here. So then when we add equations, informally speaking, when you add these together, we get negative 31x. This plus this equals 0. We eliminate the y squared terms. And these two add up to 0, although they didn't have to add up to 0 for this process to work well. Negative 31x equals 0. Divide both sides by negative 31. What's 0 divided by 2? It's 0. What's 0 divided by 3? It's 0. What's 0 divided by negative 31? It's 0. By the way, what's negative 31 divided by 0? Just checking with you. That would be undefined. That's messed up. So you couldn't pull this down. But 0 divided by negative 31, that's okay. We have x equals 0. So if we have any ordered pairs that work as real solutions, we need the x-coordinate to be 0. But then, what could y be? Do we have a corresponding value for y? Could there be more than one? Let's take x equals 0, and let's plug into any one of these 4 equations that had x or that had x and y in it. So we could plug this into here, or here, or here, or here before we touch the equations. I guess I should do this. I can take x equals 0, plug into here, plug into the top equation, plug into this equation, or plug into this equation. In my notes, I went with the first equation over here, and I'm going to plug x equals 0 into the first equation. I'll go back to the warnings in just a moment. Okay, so we have 2x plus 5y squared equals 35. Remember, we have x equals 0. Plug in or substitute in x equals 0. So it turns out we get 0 plus 5y squared. That's 5y squared equals 35. Divide both sides by 5. We get y squared equals 7. And be careful, if y squared equals 7, what can y be? Be careful. If y squared equals 7, what can y be? Plus or minus. Please remember that. I'll put that in red. Plus or minus the square root of 7. Many people forget the plus or minus. Right. So actually, if x equals 0, y could be one of 2 values, root 7 or negative root 7. Let's write both ordered pairs down. So one ordered pair has x equals 0 and y equals positive root 7. Another ordered pair has x equals 0 and y equals negative root 7. Some people might write this as the ordered pair 0, comma, plus or minus the square root of 7. Some instructors may accept that, but especially when you go on to Calculus 3, Math 252 at Mesa, be very careful because the plus or minus symbol can be misread sometimes. For example, in Calc 3, what if you see something like this? An ordered triple that goes plus or minus something, plus or minus something, and plus or minus something. Well, what would this mean? I mean, how many solutions will we have? Do we have 2 solutions? One where we take all pluses, one where we take all minuses or negatives? Or do we have 8 solutions where we could have either of these together with either of these together with either of these? So anything goes. So the plus or minus symbol can be ambiguous. Here, it's not so ambiguous. Although remember in trig, we saw identities where you said, make a choice. So if you want to be absolutely clear, then separate out the 2 solutions. Here are the 2 ordered pairs. These are the 2 solutions to our system. So again, there's a problem with potential ambiguity with this. Although the problem of ambiguity is much more severe in Calc 3, where we go, what's the deal? Do we take all the tops and then all the bottoms, or is it anything goes, or what is it? So Calc 3 might have to write things out. Now, actually, before we go on to our next example, I want to do a few things. I want to go back to my warnings, and then I want to talk graphs. First of all, remember to multiply the right-hand sides by the numbers. So over here, when we talked about multiplying through the top equation by 2 and the bottom equation by -5, remember to hit the right-hand sides as well as the left-hand sides. A lot of people, they work on the left-hand sides, they hit the equal sign, and then they stop. They get tired. Please hit the right-hand sides by these numbers as well. I guess I'll use blue here. How about black? Let's use black. Multiply the right-hand sides as well. Okay, second, why didn't we multiply the second equation by 5 and not negative 5? Yeah. So basically here we multiply by negative 5. Why didn't we multiply by positive 5? Well, remember, if you multiply by positive 5, you get a positive 10 here, and then you'd be subtracting. And remember, folks, we saw this in long division, right? We're going to see this in matrices. We saw it before with vectors also. You are much better at adding and combining like terms than subtracting. So our goals here are positive 10 and negative 10 as coefficients. We want to deal with the signs early on because you are much better at adding and combining like terms than subtracting. If you had made both of these 10s, you would have had to subtract. And some people have problems doing that mentally, especially if you have negative signs in here. Okay, we generally prefer to add. All right, so use opposites. Third, we were lucky. We were lucky that we got zeros on the right-hand side. They don't have to be zeros all the time. All right, now I want to discuss the graphs. Okay, now the real solutions to a system correspond to what points for the graphs of the equations involved. These are intersection points. Remember, these real solutions correspond to intersection points between the two graphs. Remember these two original equations. Now let's graph these. Now take a moment. If you graph these, what do you think we're going to get? And also, I want to address something else. We had x equals 0. We had one x value give us two different y values. So look at our two solutions. What I'm saying is that we have 2 points that are on both graphs, in fact, where we have an x coordinate of 0 and the y coordinates are different. So these two graphs do not represent x as a function of y because we have one x.
Actually, I want to say they don't represent y as a function of x. They do represent x as a function of y. Remember, corrections are in the descriptions.
Leading to two different y coordinates. Keep these things in mind. How would you graph these two equations? Let's see. 2x plus 5y squared equals 35. Let's move this over here. 2x plus 5y squared equals 35. Let's zoom out. Hey, look at this. It's a parabola opening leftward. See, if you were to solve this for x in terms of y, you'd be getting x equals, okay, so you have 35 minus 5y squared, but then you're dividing all that by 2. All right, so it's 1/2 times all that. And notice I just recolored the graph. These are equivalent equations. X as a function of y, all right? And I can even bring the 1/2 in. 35 halves minus 5 halves y squared, all right? So x equals, how do you graph x equals minus y squared? Remember that? X equals the opposite of y squared. That was a parabola opening to the left, right? The 5 halves does some stretching, all right? The 5 halves does some horizontal stretching, actually, and then the 35 halves moves it. All right, so we get this green graph here. Bottom line, it's a parabola opening to the left. Okay, same as this guy down here. 7x plus 2y squared equals 14. Parabola opening to the left. So look here, the blue graph and the black graph. They're both symmetric about the x-axis. That helps explain the symmetry between these 2 points, 0 comma root 7 and 0 comma negative root 7. Okay, look at these intersection points. Here's 0 comma root 7. Root 7 is about 2.6. Here's 0 comma negative root 7. So these points here are the 2 intersection points that are on both the black graph and the blue graph. 0 comma root 7 and 0 comma negative root 7. Notice the graphs fail the vertical line test. They do pass the horizontal line test. All right. Next up, how many solutions can a system have? And remember, how many solutions can a linear system of equations have? Next time.
Okay, actually, since we're going to have questions at the end of today, actually, now's a good time for a break before we go on. So why don't we go ahead and take a break? No. Why break now? Yes, a break now. All right, so let's, okay, so let's break. Okay, come back at, let's see, 8:17. So come back at 8:17. All right. And I will remember to mute. Please remember to mute, and I'll record. Okay, so I'll see you at 8:17. We'll continue with this. All right. And we have good stuff. We're going to start off partial fractions in 7/4. So if you think you know this other stuff already, hang on. Okay, you're going to want the 7/4 stuff. Definitely. All right, so I'll see you then. Okay.
Hi, everyone. So how many solutions can a system of equations have? We've seen nonlinear systems with 0 solutions, where the empty set was the solution. Remember the circle and the line? Remember that problem? We had the empty set as our solution set. We've seen 2 solutions, like the 2 parabolas, right? And we've seen 3 solutions, like in the case of that first problem we did, where we had the line and then this snake. 3 solutions. Well, we can have infinitely many solutions for that matter. We can a nonlinear system can potentially have any whole number of solutions, and it can have infinitely many solutions. Look at this: y equals sine of x and y equals 0. Basically, we're solving sine of x equals 0, and the y coordinate is 0 at those points. We're basically finding the x-intercepts for the sine wave. Let's do that. We have y equals sine of x, our good old sine wave, and we have y equals 0. I guess I should change the step size to pi over 2, right? So we have zeros at every integer multiple of pi. So at 0 and at pi and 2 pi and so forth, also negative pi, negative 2 pi, and so forth. We have infinitely many intersection points. The sine wave had infinitely many x-intercepts. So the system here had infinitely many solutions corresponding to these intercepts. Oh, by the way, a couple other notes. What if I have y equals sine of x over x? This is a famous guy in calculus. Now, this guy has the x-axis as an HA, as a horizontal asymptote. And this graph actually crosses over its HA infinitely many times. Remember, there's nothing in principle that stops a graph from touching or crossing over its own HA, its own horizontal asymptote. We don't see that for y equals 1 over x. This guy avoided his HA, but y equals sine of x over x crosses over its HA infinitely many times. And again, we have infinitely many solutions to the system. Again, it'll be at the integer multiples of pi, except at x equals 0. When x equals 0, there's actually a hole up here. There's actually a hole at the point 0, 1. And in fact, this explains part of why the derivative of sine of x is cosine of x, this hole on the graph. Anyway, let's try something else. Here's y equals sine of x. Here's y equals sine of x. Oops. I'm basically recoloring the graph, but if you consider this group of 2 equations as a system of 2 equations, every point on the sine wave is an intersection point. So the system has infinitely many solutions corresponding to every point on the sine wave. All right. Now, I have a question for you. What if we restrict ourselves to linear equations and linear systems? So think about the xy plane, okay? Think about Desmos here, the xy plane, all right? Now think about lines. Think about lines. I'll go back to the regular coordinate systems here, right? The regular scaling. Right? Think about lines. In the plane, in how many points can two lines intersect if you're dealing with the plane? In how many points can two lines intersect? Well, there are only three possibilities. There are either no intersection points, one intersection point, or infinitely many. Infinitely many. So let's think about this. Okay. How do two lines normally intersect? Well, here's a line, okay? There's one intersection point. It's like an X, right? So of course, it's possible to get one intersection point between two lines and exactly one solution for a system of two linear equations in two unknowns. But how can you get no real solutions? How can two lines never intersect in the plane? You take this line, and how about a parallel line? That's different. Hint, hint. How can I get infinitely many solutions? It was similar to what I did with sine of x on Desmos. Here's a line. Well, draw another line right on top of it. Same stupid line. Just like we had same stupid sine wave, here, same stupid line. Infinitely many points. A line and its copy. All right. So again, if you have a linear system in two space, basically, right? How many solutions could you have? Well, you could have no solutions, like here, if you have different parallel lines, in which case the system is inconsistent. You could have exactly one solution, which corresponds to the intersection point between non-parallel lines, or you could have infinitely many solutions, where you have coincident lines. Same stupid line, same stupid line. So if you're dealing with the plane, there is no way that a line, which by definition is a straight line, okay, there's no way that two lines, meaning straight lines, can intersect at exactly 2 points or exactly 3 points. That cannot happen. They have to intersect in either no points, 1 point, or infinitely many points. Same stupid line. So this suggests now some possible special cases. For example, solve this system. You don't even have to show any work. Solve the system. X plus y equals 2, x plus y equals 1. Are there any ordered pairs, x comma y? Do we have any pair of real numbers whose sum is 2 and whose sum is also 1? Can you think of two numbers that add up to both 2 and 1? Real numbers? I can't. Solution set is the empty set. We have no ordered pair x comma y that will satisfy both equations. Graphically, what happens? Graphically, how would you graph these? You can think in terms of intercepts or slope-intercept form. Let's think intercepts. What are the intercepts for this first line? 2 comma 0 is the x-intercept. 0 comma 2 is the y-intercept. So here's the graph of x plus y equals 2. What about the graph of x plus y equals 1? That has intercepts 1 comma 0 and 0 comma 1. X plus y equals 1, a different parallel line. These two equations correspond to lines that are different parallel lines. How many intersection points? 0. The empty set is the solution set. What if you try to do this using algebraic mechanics? Now, before, I mentioned how it was easier for us to add than to subtract, but I think we can hack this. What happens if we subtract these two sides from these two sides? What happens? On the left side, we get 0, right? This minus all this is 0. 2 minus 1 is 1. So here's the logic. If this system has a solution, then the solution must solve 0 equals 1, meaning 0 equals 1 must be true. Now, hold on. If the system has a solution, then the solution must solve 0 equals 1. Somehow, 0 equals 1 would somehow have to be true somehow. No. Think about the contrapositive. Remember the idea of the contrapositive? The contrapositive of if P then Q, contrapositive of if P then Q is if not Q, then not P. Switch and negate. What's the contrapositive? Do this in blue. What's the contrapositive of this statement? Well, if 0 does not equal 1, and isn't that the case? Oh, how about this? If the solution does not solve 0 equals 1, then the system has no solution, no real solution. No real solution. Oops. If the solution does not solve 0 equals 1, well, nothing solves 0 equals 1. 0 equals 1 is always false. Unless you have a weird number system, 0 equals 1 is always false. Then the system has no real solution. It's the logic. This is true from our mechanics. Therefore, the contrapositive is true. Hey, 0 never equals 1. The system has no real solution. All right, so 3 different approaches, right? Just sort of your mathematical sense way. The sum cannot be both 2 and 1. What is the solution to a system? It's got to solve all the equations. Also, if you consider graphs, no intersection points. Also, if this is going to be true, then somehow 0 has to equal 1, somehow, and that can never happen. Empty set. That's your solution set. What about something like this? How many solutions does this system have? If we covered this up, if we just had the top 2 equations, there would be infinitely many solutions. Same stupid line, right? Y equals x plus 2 and y equals x plus 2, same stupid line. Infinitely many solutions. But if you throw in this requirement, this equation, remember, a solution to a system has to make all 3 equations true. This third equation is never true. So if you throw this guy in, empty set, right there. If you throw in more equations, it's like throwing in more conditions. You can never expand the solution set. You can only keep it the same or contract it. So here we start with this, infinitely many solutions, right? Infinitely many points on the line, right? Infinitely many points along the line. Throw in the second equation, well, it's the same stupid line, right? You still have infinitely many solutions. But then you try to throw in this third equation, that kills it. So this one weak link in the chain breaks the whole chain. Empty set. Next up, how can we consider graphs of linear equations in 3 space? It's no longer lines. What are they going to be? Next time.
All right. So, okay, well, I'll play a little bit of this next piece. What are they? How do you graph these things?
Hi, everyone. A few comments about systems of linear equations in 3 unknowns, x, y, and z, let's say. In section 8.1, we'll solve this kind of a system using matrices, boxes of numbers. And these equations are going to be graphed in 3 space, not as lines, but as planes. Imagine a piece of paper extending infinitely far. Now, these 3 equations we can graph in GeoGebra.org. Look under New Math Apps, 3D Calculator. The x-axis here is in red, the y-axis is in green, and the z-axis is in blue. The way it's oriented now, it's like if you look in this direction, You're looking down on the XY plane if you look like so. But on a whiteboard, typically we would orient things so that the positive x-axis is actually kind of pointing at you. And then the y-axis and the z-axis, the YZ plane, would be the whiteboard. So we tend to draw it like this, where the positive x-axis is pointing at you. Here, I use that orientation, and I typed in the three equations from the system here. The graph of this first equation is a plane. There's even a little note here, equation 1. By the way, to change the color, you can go to settings, color, you can change the color, you can change the style, put in lines, grid lines. All right. The second equation gives us a plane in red. And notice that the blue plane and the red plane intersect in a line. Equation 3, that's going to intersect that line at a point, and the point is the common point of intersection. -6, 8, 2. It turns out that's the solution for the system. We'll find that in 8.1. I'll rotate this around, and you can see how this point lies on all three planes. And in order to have a solution to this system, we need a point, a solution point, to lie on all three graphs. The point has to lie on all three graphs. It's not enough just to lie on 2 of them. For example, here, the blue plane and the purple plane intersect in a line with infinitely many points, but the only solution is this point, this blue point, where we're also intersecting with the red plane. This blue point is where all three planes meet. It's the sole solution in the solution set. For these linear systems, we can only get no solutions. Imagine parallel planes, like in a science fiction story. No common points of intersection. You could have one intersection point, like we did in this example here, or infinitely many solutions. For example, maybe we have the same stupid plane. 1, 2, and 3, same stupid plane. Or for that matter, we could have a plane on top of itself, and there's a third plane coming in that gives us a whole line of solutions. We'd have infinitely many solutions, but on a line. Okay, now I'd like to go back to the original setup. Let's reorient these. Okay, so together, the x-axis in red and the y-axis in green make the xy plane. That has equation z equals 0. Kind of hard to see here. So it's kind of hard to see, but in blue, okay, that's like the floor. That's the xy plane, z equals 0. It contains the x and y axes. Oops. Now, x equals 0 is the yz plane. I'll put that in red. X equals 0 is the yz plane. That's like the whiteboard. It contains the y-axis and the z-axis. Y equals 0 gives us the y equals 0 gives us the xz plane. It's like a wall on the side. Put that in purple. All right. So y equals 0 is the xz plane, which contains the x-axis in red and the z-axis in blue. And what is their common point of intersection? What's the solution to this system? X equals 0, y equals 0, z equals 0 is going to be the origin. That's the point where all three planes meet. And these three coordinate planes, z equals 0, the floor, x equals 0, the whiteboard, y equals 0, this purple wall here. These three coordinate planes will divide 3 space into 8 octants. Here's octant 1, where everything's positive. Okay. We have 4 octants. Whoops. All right, hold on. There. We have 4 octants above the blue xy plane, z equals 0, and we have 4 octants below the xy plane. The 3 coordinate planes divide up 3 space into 8 octants. Let that sink in. All right.
Okay, so I'll just pause this for a moment. So remember, how do you graph linear equations in 3 space? Okay, now with section 7.4, partial fractions, this is going to be new for many of you. Now, it's like dipping your feet in, it's like jumping into cold water. You start with dipping in your feet, right? And you know, a lot of students get nervous at first, but then you get really good at these. So by the time a final exam would come around, conscientious students who have worked the homework, they would do well in these problems. So the whole stuff with 7.4, we're going to introduce them today with PFD forms, okay, forms for partial fractions, and we're partial fraction decompositions. And after the end of today, you'll be able to do all the homework through 7.4 number 1. Okay, so by next Tuesday, I encourage you to do 7.4 number 1, maybe even before you do the 7.1 to 7.3 block. Okay, you might want to do 7.4 number 1 as your top priority once you finish your 5-6 homework. All right, so partial fractions or PFDs, partial fraction decompositions. It takes time to get used to, but you're going to get good at it as you work through all the homework problems. And there are a lot of homework problems. It's almost like A through Z. I'm not kidding. Not quite Z, but it's a lot. All right, let's start this off.
Hi, everyone. We're going to start section 7.4 on partial fractions. And this will eventually involve systems, in case you're wondering what this is doing in chapter 7. Well, what are these things? What are partial fractions? You're going to get to know these very well in Calculus 2, Math 151, because you're going to have a section on integration by partial fractions. So you will see this in your Calc 2 class. Okay, let's start with a review example. So in the beginning, in your old school algebra class, you might have taken these 2 rational expressions and subtracted them. 3 over x minus 4 minus 2 over x plus 1. Your first step would be to find an LCD, a least or lowest common denominator. Here, since these guys have nothing much in common besides plus minus 1, we take their product. Just like if we had 1/2 minus 1/3, we would take the product of the denominators, 2 times 3 or 6, is our LCD. Now, as we build up the fractions so that we get this common denominator, right, we can take this first fraction and build it up. And to do that, we ask, who's missing? Who's missing from this denominator as we form the LCD? Well, the x plus 1 is missing. So why don't we multiply the top and the bottom by x plus 1? The fraction bar already groups the top and the bottom, but for good measure, we can do this. Maybe this too, right? And then, to build up this fraction, right, I'll put an arrow here. Who's missing from this bottom? Well, the x minus 4. So we'd multiply this fraction by x minus 4 over itself. Again, optional grouping symbols, but they're nice to see. So when you multiply these guys together and multiply these guys together, you get a common denominator and you subtract these numerators. 3 times the quantity x plus 1 minus 2 times the quantity x minus 4. Again, one shortcut is to just write the LCD down here, and then for the tops, the numerators, you attach who's missing. For this fraction, x plus 1 was missing in the denominator, so he's part of the buildup when you build that fraction up. Here, x minus 4 is missing in the bottom, so you put the x minus 4 up here as part of that buildup. Think who's missing when you think about the pieces that have to be attached to these tops. All right, and then you distribute on top, combine like terms. When you subtract these rational expressions, you get this over here. X plus 11 over x squared minus 3x minus 4. So back in your algebra classes, you may have done that. Subtract these rational expressions and get this uglier looking guy down here. We're now going to do the inverse problem. What do I mean by that? The inverse problem. I give you something like this, and your task now is to break this guy up into a sum or difference of smaller, nicer fractions. So we go in reverse. I give you this ugly fraction, you decompose it into a sum or difference of nice partial fractions, which will be easier to integrate. And in calculus, you integrate term by term. So this is helpful. These guys you can integrate pretty easily, but you had to break this guy up first. Now, your ability to break this up into a sum or difference of partial fractions, that's going to depend on your ability to factor this denominator over the reals. So make sure you remember how to factor. And it turns out that there's going to be one unique way you can decompose this as a sum or difference of the kinds of partial fractions we're looking for, although you can switch the order. So again, the PFD form, how do we reverse this process? What we're talking about here is called a PFD, not PDF, like a file on a computer, not PDF, PFD, partial fraction decomposition. The PFD for this uglier fraction is this over here. We're decomposing this, we're breaking this up into a sum and or difference of these nicer partial fractions. The PFD form that we need will depend on the factored form of the denominator. So I know that once I factor this guy, I'm going to need a number over x minus 4 plus or minus a number over x plus 1. So once we know how to factor the denominator, we should be able to figure out the PFD form. And in fact, that's going to be problem 1 in your homework for this section. It's important that you know how to figure out the PFD form, because if you can't figure this out, then you're going to be dead if you have to do more, if you have to actually figure out the PFD over here. You have to know how to work out the PFD form. What form will this decomposition take? Okay, so I'm going to go straight to an example here. If we factor a polynomial with real coefficients over the reals, what potential cast of characters might we be looking at? Now, of course, on homework and exams, I would never ask you to factor a monster like this thing. But in principle, how does this thing factor? And what is the anatomy of the factorization? How bad could the factorization get? What are the potential pieces when you factor this kind of polynomial over the reals? All right. It turns out that this hideous polynomial ends up factoring like this. And I want to talk about the cast of characters here. If you factor a polynomial with real coefficients over the reals, what could be your cast of characters? And we're going to go through these one by one. And once we understand what these factors are like, once we categorize these factors, then we can talk about the PFD form that we're going to develop. And then later on, how can we actually get the PFD? All right. The cast of characters. So here's what I'll do. I'll leave this up here, and I'll make a copy. All right. And we'll talk about the cast of characters. Okay, first up. The 3 here is a constant factor. Sure, your final factorization could have a constant factor, like 2, 3, 4, and so forth. It could be 1, in which case you don't need a number out here. X squared is actually surprisingly tricky, and we're going to deal with that later on. We'll discuss x squared last. Surprisingly, he's the trickiest one to categorize. X minus 3, what do you call a first degree polynomial? You call it linear. And it's a distinct linear factor in the sense that there's no exponent here. We don't have copies. We don't have a square or a cube up here, for example. We don't have copies. We just have this distinct linear factor. It's all alone. Oh, and by the way, if you see 2x minus 6, make sure you factor out a 2 first. Okay, make sure you don't have copies in disguise. 2x plus 1, well, that's also a distinct linear factor. It's just not monic. There's actually a number in front of the x besides 1. But both the x minus 3 and the 2x plus 1 are distinct linear factors. There are no exponents on the top here. And they're both first degree. Now the square of x plus 4, see here we have 2 copies of x plus 4. So we don't have distinct linear factors over here. For the square of x plus 4, we have a nice power of a linear factor, like a square or a cube of a linear factor. And we can think of this as x plus 4 times itself. So we can think of the square of x plus 4, the cube of x plus 4, and so forth as a case of repeated linear factors. X squared plus 1, that's not linear, and we cannot factor it further over the reals. It's prime. So we're going to call x squared plus 1 a distinct R irreducible quadratic factor. Or in other words, it's a distinct quadratic factor that's prime over the reals. This sounds very technical. Prime over the reals. It's a distinct quadratic factor that's prime over the reals. It's distinct because we don't have a square or a cube on top of here, for example, right? It's prime over the reals because this cannot be factored further over the reals. In the case of a quadratic, you can tell if a quadratic with real coefficients can be factored over the reals, depending on whether or not this has real zeros. If this has real zeros, we can factor this further over the reals. But x squared plus 1 has no real zeros. So we cannot factor this further over the reals. Finally, the cube of x squared plus 4. This time we have the power of a quadratic that's prime over the reals. Or we have repeated factors of that type. The cube of x squared plus 4 is a nice power of an R irreducible quadratic factor, or a quadratic factor that's prime over the reals. And because this can be rewritten as 3 copies of x squared plus 4 all multiplied together, we can think of this as an example of repeated quadratic factors that are prime over the reals. Finally, what is the deal with x squared? You might think, oh, that's quadratic. But the thing is, it has real zeros, right? Namely 0 and 0. X squared can be thought of as, well, if you were to ask an algebra student, or if an algebra student asks you, what is x squared? You might say x times x, right? X times itself. X squared is not prime over the reals. X squared actually represents repeated linear factors because it can be written as x times x. In that sense, it's not prime. You can write x squared as x times x. You could think of this as the square of x minus 0 if you want to stress the fact that we have repeated linear factors. X squared, repeated linear factors. Think of it as x times x. It's not prime because 0 is a 0 of this quadratic. Again, we do not consider x squared to be R irreducible or prime over the reals because it has a real 0 or root, namely 0 itself. You can think of x squared as this, the square of x minus 0. So we've seen our cast of characters. Once again, what are these? A constant factor times, what are these? Repeated linears, distinct linear, repeated linears, a quadratic factor, prime over the reals, and powers of those. Repeated quadratics that are prime over the reals. Oops. again, let's type these out. 3 is a constant. X squared, again, surprise, repeated linear. It's x times x. X minus 3, that's going to be a distinct linear. Same with this guy here, distinct linear. The square of x plus 4, again, repeated linear. So the square of x plus 4 was like x squared. X squared plus 1, once again, it's a quadratic that's prime over the reals. And here we have repeated. Repetitions of such factors. Repeated quadratic prime factors. Repeated quadratic prime factors over the reals. All right, our cast of characters for that hideous polynomial. But once you factor a polynomial completely over the reals, and you might get any number of these guys here, you can then figure out the PFD form. All right. By the way, if it's improper, if the degree of the top is not less than the degree of the bottom, we'll end up having to do long division. All right. If the rational expression is improper, okay, we'll have to do long division. We'll talk about that later. Now, my general comments here about PFD forms, they're textbook-like, good bedtime reading, perhaps. I'm going to go straight to the example. All right, find the PFD form for this over here. It's a bit too involved for us to find the actual PFD, but let's find the PFD form. And what do I even mean by that? Okay, it means that we don't have to solve for the unknowns. All right, here's the idea. What are these guys? X squared is what? Repeated linears. This guy here is what? The square of x minus 4. Also, repeated linears. What's x squared plus 1? It's not linear, and we cannot factor this over the reals. It's a quadratic with no real zeros. This is a quadratic that's prime over the reals. All right. So again, the cast of characters. X squared, repeated linear factors. Same for the square of x minus 4, but x squared plus 1. It's not linear, cannot be factored further over the reals. It's going to be quadratic that's prime over the reals. All right, repeated linears. It turns out that these various factors will correspond to various partial fractions over here, or forms for partial fractions. Because we have an x squared in the denominator, we're going to run up to the power. What do I mean by run up to the power? We write x and then x squared. Because of the x squared, we have a fraction, a partial fraction with x in the bottom, and another partial fraction with x squared in the bottom. If we had x cubed here, we'd have another fraction, like plus c over x cubed. A, B, C, and so forth are going to represent real numbers that are unknown at this time. But from the x squared as a factor on the bottom, we get a over x plus b over x squared. These are the partial fractions we get from the x squared. Don't forget to put the plus sign there. Even though eventually b could be negative, that is possible. All right, now in blue, we have the square of x minus 4. Again, we run up to the power. We have x minus 4 all to the first, and then x minus 4 all to the second. If that were cubed, we'd have another fraction with x minus 4 all cubed down below. And again, we have constant forms on front. Remember, A, B, C, and D are all going to represent real numbers. We just don't know them yet, what their values are. Finally, in green, x squared plus 1, our quadratic that's prime over the reals, x squared plus 1. Because of that, we get this guy here. We copy him down below, x squared plus 1, but be prepared for a linear form on top. Not just constant. We could have something as bad as a linear form up on top. What do I mean by linear form? Think slope-intercept form. What was slope-intercept form? Slope-intercept form was y equals mx plus b. Well, similarly here we have ex plus f. You have your choice of letters, but of course don't use x again, and make sure that you don't get any copies. A, B, C, D, E, F, where these represent real numbers, we just don't know them yet. And it's almost like a combination lock on a locker. There's only one sextuple. There's only one sequence of 6 real numbers for A through F that will unlock this thing and will make this whole thing equivalent to this fraction over here. Oh, by the way, and if there's a square over here, you'd have another fraction. If you had a square there, in fact, I'll put it in. If you had a square here, put this in brown. If you have a square here, then you would have another, kind of hard to see. How about a bright purple? Okay, if we have a square here, all right, then we get another partial fraction. Again, we run up to the power. We have x squared plus 1, all squared in the bottom. We run up to that power. And on top, we have another linear form. What would you use? Linear form. Think slope-intercept form. You could use gx plus h, where g and h represent real numbers, but they're unknown. Here's the PFD form. So at this point, you can go up through 7.4 number 1 on the homework that deals with PFD forms. For a problem like this, I would not ask you for the values of A through F, or certainly A through H on an exam. That would be too involved. But the form is fair. I can ask you, what's the PFD form for this big ugly fraction over here? The PFD form is fair, but I would not consider the PFD fair. We have 6 unknowns here. I would not give you a problem where I would require more than 4. All right, later on, we're going to get more practice with these forms, and also how do we find the actual values for A, B, C, and so forth. So what is, in a way, the combination that would work, really the sequence of numbers that would work to unlock this whole thing? That's later on.
Okay, so again, by next Tuesday, I would encourage you to do 7.4 number 1, even before the rest of chapter 7. All right, so that's all the new stuff for today. It was quite a bit though, right? That's all the new stuff for today. So we're at 9 o'clock right now. All right. And first of all, any general questions before we go on to specific questions? Any general questions so far? General questions. Okay, so I'm going to pause the recording at this time. So, okay, so I'm going to pause at this time. And I'm going to give you 5 minutes. So let's reconvene at 9:06. Okay, in the meantime, you can ask me questions. You're probably going to give me a list of questions in chat. That's fine. Remember that these questions have been addressed in previous videos, although I do have my notes on these. So if necessary, we can go over them. So let's do that. Again, let's pause. Okay, so again, if you want me to pause or stop the recording, let me know. But in the meantime, as you know, students appreciate it when we can record what we can. Let's see. Well, I'll go ahead and cut the video here. All right. Okay, so here's from a student. Oh, right. Okay, so let me address that issue. And this comes up from time to time in a calculus class. So I want to address this issue. So this is, I guess this is 5.2, right? 5.2, like an E on 5.2. Yeah.
Yeah.
Right. Okay. So, and in fact, I think I have, I think I have this, as part of my notes here. Right. 521E. Right. Okay. And if anyone wants me to review this, this isn't a video, but if anyone wants me to review this, in fact, this was in 521E. That was I went over that last Thursday after class. So it's in the class after class video part last Thursday. So if you want me to review that, I can. Where we want to verify that the left-hand side, which was basically this piece over here, right, equals this over here. All right. Now, there's an issue which does come up from time to time in calculus, where some students were curious, why is it was okay for us to remove absolute value up on top here? And basically, it's in blue over here. All right. So explaining why is it that the absolute value of 1 minus cosine of theta is equal to 1 minus cosine of theta, you don't need the absolute value. All right. Well, here's the idea. The absolute value of 3 is 3. The absolute value of 7 is 7. The absolute value of 0 is 0. The absolute value of any non-negative value is itself, right? The absolute value of A is A if A is non-negative, all right? Well, how come we're guaranteed that 1 minus cosine of theta is non-negative? How am I guaranteed this over here?
Oh, right, I remember. It's because of the domain.
Right. Well, it's a range issue.
Oh, range.
Right. Okay, so why is it that 1 minus cosine of theta is guaranteed non-negative, and therefore we can remove absolute value? It's because, let's say that I have $1, right? And you take cosine of theta away from me. Well, the most that can be is 1, because the range for cosine of theta is from -1 to 1. So if I have $1 and you take away cosine of theta from me, you're taking away at most $1, which means that I have either positive or 0, but I don't have negative. I don't owe you anything anyway. but 1 minus, but because cosine of theta is between -1 and 1, in particular, cosine of theta is never more than 1, right? It can't be 1.1 or 1.2 or 2. Then 1 minus cosine of theta is guaranteed non-negative for all real values of theta. Therefore, as a simplifying step, it's conventional that we drop the absolute value because they're unnecessary. Because the argument 1 minus cosine of theta is guaranteed non-negative. Okay, therefore, as a simplifying step, we remove absolute value. However, sine of theta can be negative, so we keep the absolute value there. And basically, this is part of explaining why some of those half-angle identities worked for tangent, but it was kind of difficult to see why tangent of half theta had the same sign as this without the absolute value. That was tricky to see. But I was hoping that people could at least work out the mechanics to get from here to here. Any questions about that? Because that observation does come up sometimes in calculus. 1 minus cosine of theta is always non-negative. Same thing for 1 minus sine of theta. It's really a range issue. All right, questions about that? Questions? All right. Any questions there? Any questions there? So that was a sort of a conceptual questions about range. Right. Okay. So and again, I have the full video for 5.21e explaining this in detail in last Thursday's video. Although if anyone wishes, I can go. I mean, I can kind of sketch this out quickly, right? It's kind of a trig conjugate idea, but also you can see that if you multiply this by its twin, that has the impact of basically removing the radical on top. We start with absolute value because of this. Wait, where's that? Yeah, yeah, because of this rule over here. The square root of x squared is absolute value of x. We can drop the absolute value up on top. All right. Also, on the bottom, you can see that we're trying to force a Pythagorean. When you multiply this by the trig conjugate, we get 1 minus cosine squared theta, and by a Pythagorean identity, that ends up being sine squared theta. And then by the same absolute value rule here, this becomes absolute value of sine of theta. Unfortunately, we're not able to remove absolute value there because sine of theta can be negative. All right, that's the sketch. All right. Okay, so I see that I have a couple of questions in chat, and some of these are private messages, but I see here 5.3 numbers 2 and 3, and 5455 numbers 7. All right, so let me address those. Let's see here. Okay, let's see here. 5.3, let me see. Okay, so I've not done these yet. All right, so let's go to blue. All right, get the questions. All right. Okay, so first off, let's do I'm recording, right? Yeah, I'm recording. Okay, so 5.3, number 2. Ah, yes. Okay, this over here. Okay, so let's start with this. 5.3, number 2. Okay, consider the equation tangent of x equals 2. All right. Oh, okay, so this is 5.3, number 2. All right. Tangent of x. All right. Okay, so whoops. All right. Okay, so tangent of x equals 2. All right. First of all, find the solutions of this equation in the interval from 0 to 2 pi. So I like to consider the unit circle. All right. Now, 2 is legitimate tangent value, right? The range of tangent is all real numbers. 2 is a slope. It is a tangent value. So this will have real solutions. All right. Now, notice that 2 is positive, right? In what 2 quadrants is tangent positive? In what 2 quadrants is tangent positive? We have this steep line segment, right? Like this diameter here, all right? Quadrants 1 and 3, correct. Quadrants 1 and 3. We associate those quadrants with positive slopes if you consider like lines or line segments that go through the origin, all right? So what's my acute solution over here? Well, my acute solution is basically given by the inverse tangent of 2. And remember, the ranges for inverse sine, inverse cosine, and inverse tangent will always include the acute angles. So we know that if I want this acute angle, this reference angle, inverse tangent of 2 or arctangent of 2 will do it. So that's going to be a key. All right. And then how do I get from this angle to this angle over here? How many radians do I add? Well, how many radians are in a half revolution counterclockwise? All right, well, we take inverse tangent of 2, and we add how many radians? Not 2 pi, but just pi. All right. So then I say find the solutions. Technically, it's nice to write the solution set, right? So it is ideal to write down the solution set where you have inverse tangent of 2 as one solution, comma, inverse tangent of 2 plus pi as the second solution, and braces. Okay, let me check that for a moment. Right. So arctangent of 2 or inverse tangent of 2, same thing, and then pi plus that. All right. Again, I encourage solution set form because you're solving an equation. All right. Any questions thus far? Questions thus far? Okay, so that's 2a. 2a. Okay, now what about, oh, okay, now 2b, just use your calculator, right? So use your calculator. Make sure you're in radian mode. Okay, make sure you're in radian mode. So on part B, make sure you're in radian mode. Okay, remember the assumption is that, especially for chapter 5, that the outputs, the results for inverse sine, inverse cosine, and inverse tangent are given in radian measure. They're like angles in radian measure. Now in chapter 6, I realize that we often accept answers in degree mode. That's fine. But in chapter 5, you're really dealing primarily with radian mode. That's the assumption. All right. Okay, so I see an wait. Okay, you're okay. All right. Okay. Okay, yeah, okay. So part B, make sure you're in radian mode. And I think my answers are correct here. Many semesters of students have checked my work. So arctangent of 2 or inverse tangent of 2 is about 1.107 radians. Remember, you don't have to write radians. And then when you add pi, see, you're adding about 3.14. You get 4.249. I tell you to round off to 4 significant digits. So these are both round off to 4 significant digits. All right. Okay. And then in C, find all real solutions of the equation. All right. Well, actually, whoops. Because of the rotational symmetry, all right. So in part C, I'll note this in red here. So for part C, well, okay, how do you get all real solutions, right? Well, you have arctangent of 2 or inverse tangent of 2, and you basically keep rotating by half revolutions. Okay, so that's why for the solution, for the general solution set, you can take arctangent of 2 or inverse tangent of 2 and add pi n. That means that you add integer multiples of pi, right? N can be negative also. And that means that you're adding or subtracting by half revolutions by these integer multiples of pi. So these would be good forms for the solution set. Arctangent of 2 or inverse tangent of 2 plus pi n, where n is integer. All right. Okay, now for 3, I'll start this off and then let's see if you can complete it. Remember, we have all day on Thursday to review. So let's do this in purple maybe. Okay, let's start number 3 in purple. All right. Okay. So this will be 5.3 number 3. Okay, 5.3 number 3. Okay, let's start this off. All right. In fact, I might encourage you to do a substitution. This might help. You don't have to do it, but maybe you let u equal cosine of x. That might be helpful. All right. And then the equation you see here, I'm keeping it in purple, right? Okay. So the equation you see here for number 3, all right, when you do the substitution, you're going to get 5u, whoops, 5u, sorry, 5u squared minus 14u minus 3 equals 0. And it turns out you can factor this old school over the integers. 5u squared breaks up as 5u and u. I think I'm going to have something with a 3 here, something with a 1 here, because we have 15u and 1u. It's heavy on the negative side. So I'm thinking it's a negative 3 here because 5u times negative 3 is negative 15u, because the factoring gets people here. And then here, plus 1, we have plus a 1u. And you can see negative 15u plus 1u is negative 14u. All right. So we can factor this old school like this. All right. And then you would set each of these factors equal to 0. 5u plus 1 equals 0. or u minus 3 equals 0. Solve each of these for u. Subtract 1 on both sides. Divide by 5. U equals negative 1/5. Over here, add 3. U equals 3. Yeah, and you know what? I have to tell you folks, substitution, if you look at my notes, like in chapter 0, I don't substitute as often as I could have. So I found myself, substitution helps me a lot too. Otherwise, you look at this mess and go, oh my gosh, what do I do? Even me. All right, so over here, we're done with most of the algebra phase, okay? And then you want to go back to the trig phase. Remember, u was cosine of x. Cosine of x is negative 1/5. Cosine of x equals 3. Now, wait a minute, though. Wait a minute. Cosine of x equals 3. Do you know any angles whose cosine value is 3? Do we pick up a horizontal coordinate of 3 on the unit circle? Is 3 in the range of cosine of x? That's a dead end. That's a dead end. All right. The solution set to this here is the empty set. But negative 1/5 is a legitimate cosine value that is in the range, okay? And I'll give you a hint. You can use inverse cosine to deal with this. Now, the question I want to ask the student, and this is fine. Would you like me to proceed? I could, but a key hint is that you use inverse cosine, but I can proceed here if you would like me to. Would you like me to proceed? Okay. Okay, so let's talk about this. I'll bring up another page. I like this, free whiteboards. All right. So I'm focused on cosine of x equals negative 1/5. All right, thank you. Let's see. So first of all, we want to look at the solutions between 0 and 2 pi. All right, so I'll break out the unit circle now. Maybe I'll put this in what? Purple? All right. In what two quadrants is cosine negative? Negative. Now, x here is the angle here. Cosine of x is the horizontal coordinate. It's like x for the circle. But remember, the x here is an angle. In what two quadrants is cosine negative? Well, we're kind of looking at this point over here and this point over here, where the horizontal, kind of like x for the circle here, is negative 1/5. It's quadrants 2 and 3. Okay. You don't have to label the quadrants if you know the points, but basically we're focused on these key points in quadrants 2 and 3. All right. Now, how can I get this point over here? Well, for this point over here, we can use inverse cosine or arc cosine of negative 1/5. There's some books that might rewrite this, but I'm okay with this. Inverse cosine of negative 1/5. All right. Now, you might say, well, hey, if I go, I'll put this in blue, in green. If I go clockwise, a representative for this point would be the opposite of inverse cosine of negative 1/5. That is a representative for this point. Now, the problem is, okay, we want solutions for part A between 0 and 2 pi. Remember, we're doing part A here, all right? So this here is a negative angle. Question, how can I get a coterminal angle? How can I get a coterminal angle? By adding how many radians? By adding a full revolution, by adding 2 pi radians to get a coterminal angle. And therefore, my solution set, I hope this is a solution set. Yes. Actually, see, I have many possibilities because there are many ways of thinking about this. I picked this one, basically. Inverse cosine or arc cosine of negative 1/5, and then 2 pi minus that over there. Although there are various ways of writing it. For example, some books might like this form because it considers arc cosine of positive 1/5. Okay, that's basically the reference angle. The reference angle is arc cosine of 1/5. That's the reference angle in quadrant 1. Okay, so but there are various ways of getting the solution set here. What I showed you was that. Again, you can use your calculator to approximate these. Make sure you're in radian mode to approximate these two. Now, bear in mind, you're going to get these regardless of which of these you take. You're going to get these in radian measure. That's one of the advantages of the decimal approximations, right? Because all of these will boil down to basically this. And if you switch these, that's okay. And then in part C, you can actually do plus or minus inverse cosine of negative 1/5 because we allow negative angles. And then plus 2 pi n, that picks up all the coterminal angles. So the most efficient way to do it is probably this over here. Although, again, there are other ways of doing it. All right. So any questions there? Let's see. Okay, good. All right. Okay, going on to, let's see, some public ones here. Okay, 5455, number 7. All right. Well, I should have done that. That's okay. All right. Okay, 5.4, basically, number 7. Okay, 5.4. Well, 5.4, 5.5, number 7. Okay, so let's take a look at what this is. Okay, is it this one? 5.5455, number 7. Oh, yes, this one here, yes. Yes, good for the algebraic manipulations here. All right. Oh, yes. All right. So in green, all right, maybe I'll just go ahead and put this in green. All right. Simplify this. All right. So what I'm going to do is I'll call this star. Okay. So the given problem, the given expression, I'll call star. Okay, you should recopy it technically. Okay, I'm mostly going to recopy it over here. I can do straight lines, right? Yeah, there we go. Okay. All right. Okay. Now, I'm going to recopy. Oh, actually, you know what? Once again, why not do a substitution? Let u be 2x. Let u be 2x. All right. And then I'm gonna rewrite this with that substitution. Okay, so then I'm gonna get sine of u cosine of u all over 3 cosine squared of u minus 3 sine squared of u. All right. Now you look at the bottom and you go, okay, well, what can I factor out here? I can factor out a 3. And then you might recognize what's left as part of an identity. Okay, so let's factor out, whoops. I'll copy the top. We can do straight lines now. All right. Let's copy the top, and we have sine of u cosine of u, right? And on the bottom, we can factor out a 3, bracket, cosine squared of u minus sine squared of u. All right. Now, hold on. You should recognize this. Okay, you might have to look at the list of identities I showed you, But does that look familiar? Now remember, cosine squared u plus sine squared u is 1 by Mr. Pythagoras. This is cosine squared u minus sine squared u. Do you remember the identity for that? What was equal to that? I'll give you a hint. It was a double angle identity. Do you know what that's equivalent to? I'll give you a moment. Which double angle identity gives us this? Cosine squared u minus sine squared u. The cosines minus the sines. Well, it
Double
is.
angle identity?
Sorry?
Was it double angle identity?
Yes, double angle. Which one?
Cosine 2
Correct.
theta?
Correct. It's cosine of 2u.
Hmm. Right.
So cosine of 2 is cosine squared u minus sine squared u. And there were 2 other variations. Very good. So let's write that.
Are you applying at the bottom or at the top?
The top, I'm still going to work on the top later.
Okay.
But okay, so sine of u, that's also there's also be an identity there. Sine of u, cosine of u on top, over 3. Hey, all this becomes cosine of 2u. Any questions thus far? Questions thus far? All right. Now, and I can go ahead and do this in the same step. I'll do this in blue. Sine of u, cosine of u. Wait a minute. I remember an identity, but the identity involved a side that had what number in front of this, right? We had a double angle identity that had a number in front of sine of u, yeah, a 2. All right. Wouldn't it be great if I had a 2 in front? But wait a minute. It's not fair just to multiply the top by 2. What else do I have to do? I think you know what to do. You don't have to type it out. If you multiply the top by 2, you got to multiply the bottom by 2. Put a dot there or something. Okay, because it's always legal to multiply by 1. Here, I'm basically taking the guy in green, the fraction in green, and I'm multiplying by 2 over 2, which is 1, right? 2 over 2 is 1. We can multiply by 1 like that, right? Now, why am I doing this? Well, hey, what is 2 sine of u cosine of u? I mentioned that's a double angle identity. It's not cosine, it's what?
Sine.
Correct.
2.
Sine of 2u, correct. 2 sine of u cosine of u was the right side. So here I'm asking you to go from right to left, because normally the way you think of it is sine of 2u is 2 sine of u cosine of u. Now I'm asking you to go in reverse. That happens sometimes, like the log properties, right? Okay, so now let's continue. All right, so moving this over. All right. Okay, so we have equals. All right, so on top, okay, on the top, we have sine of 2u. 2 sine of u cosine of u boiled down to sine of 2u. Down here, 2 times 3 is 6. Cosine of 2u. All right. What is sine of 2u over cosine of 2u? The quotient identity.
6 tangent?
Okay, so first of all,
right?
okay, sine of 2u over cosine of u is tangent of 2u. Be careful. The coefficient is not 6. It is, see, the 6 is on the bottom. The coefficient is not 6. It is 1/6. Because the 6 is on the bottom. The 6 is on the bottom. Okay, and I know that's the answer because I've done this problem many times in the semester because students always ask about this question, which is fine. Here are the answers, all right? But I remember it. I remember it's the answer. Yeah, tangent of 4x over 6. Wait a minute, I forgot to sub back. We're not done yet. Forgot to sub back. U is our creation, right? We forgot to sub back. Don't forget to sub back. 1/6 tangent of twice. What was U? U was 2x, remember? U is 2x. Twice 2x is 4x. Actually, you don't need this line. Okay, you can go straight from here to here. That's fine. 1/6 tangent of 4x. One-sixth tangent of 4x. Here I put it as a single fraction. Of course, that's fine. Okay, you can put the tangent of 4x up on top if you wish. Any questions about that?
No.
Okay. So yes, students often ask for this every year, right? And conscientious students ask for this question. No problem. We go over it. Any questions? Anyone? Any questions? Okay, so 5.5, 9 through 12. Let me check these over. Oh, okay, any questions about this before we... You can see why I saved these. I'm going to save these.
I have a question, not on that, but I asked for 9 through 12, and I
Right.
tried to do 9, couldn't do it. So then I went to 10, couldn't do it, and then so on until 12. And I did the rest of the chapter before, but I'm just stumped on these 4 questions. I don't know why.
Okay, so let's see. 5 point, this block again, 5.5, the 5, 4, 5, 5 block, the 9 through 12. Oh yeah, well, yeah, these are they're different flavors here. I will say that number 10 involves a right triangle. If you look at my notes, number 10 involves constructing a right triangle. So basically,
Yeah, I saw the notes and I still couldn't figure it out. I was trying to, I put them like right next to each other, and I was trying, but I just couldn't understand how the triangle related to that.
okay, so let's start off number 10. All right. So in fact, we can try to start you off here, and then let's see if you can proceed from there. Okay, so let's get a new whiteboard over here. Okay. Okay, let's start with number 10, the 5, 4, 5, 5 block, number 10. Let's go to blue. All right. 5.4, 5.5 block, number 10. All right. Okay, so this one over here. Rewrite sine of 2 arcsine of x as an equivalent algebraic expression and assume there are no domain problems. All right. So we have sine of, and seriously, one advantage to writing it this way is that there's no special typesetting. It's easy to write that out. 2, okay, sine of, I'll space it out. Sine of 2 arcsine of x. Okay, we want to simplify that. Once again, substitution could be your friend. All right. So let's say that arcsine of x is, sometimes I use theta because I like to think of the arcsine results as being like an angle, but I think u might be more familiar. But well, you use either u or theta, okay? Because again, I normally associate with the values of these with angles, but I think u is a more popular substitution letter. All right, but who cares? Don't worry about that. That's not the big deal. All right. Oh well, I can actually still typeset it actually. All right, so we have equals, when you do the substitution, sine of 2u. But now wait a minute. What's the identity for that? We just covered that in the previous problem. Sine of 2u equals what? What is the double angle identity? Sine of 2u.
2 sine u cosine u.
Correct. Okay. All right, so 2 sine u cosine u. Let's see. All right. Now, an observation. I'll put this in purple. Okay, so now normally, see, I normally write like this, let u equal the thing that you're substituting for. But actually here, I think it's easier if you write it like this. And you do this in calculus too anyway. Let arcsine of x or inverse sine of x equal u. All right. Now, given that, what must be true? It's like the inverse statement. All right. If arcsine of x is u, then sine of what is what? If arcsine of x is u, sine of u is x. It's kind of like the zigzag back in chapter 3. Sine of u equals x. All right. Better known as, because it helps to think of this as a fraction, x over 1. Okay. You agree we can always write x as x over 1. And that helps with the SOHCAHTOA deal. All right. In green, I'm going to draw the corresponding right triangle. Pretend that's a right. That's horrible. Right triangle. There you go. Here's my angle u. Remember, u here represents an angle here. Okay. Let's set it up. Let's set up this model right triangle. So sine of u is x. SOHCAHTOA. So sine is opposite over hypotenuse. Oh, here's opposite. Opposites here. X. Here's the hypotenuse, 1. All right. Now, by the way, right off the bat, hey, sine of u equals x. Sine of u equals x. Right here. Sine of u equals x. So I've made that algebraic right there. Sine of u equals x. Now, the question is, what's cosine of u? That's the question now. How can we express cosine of u algebraically? Well, SOHCAHTOA, I'm going to need this adjacent side, all right? And then how do I find this? This is b, for example, all right? How do I find this? From whose theorem?
Pythagorean.
Pythagorean. All right. Now, I trust that you can work that out, okay? So by the Pythagorean.
Yeah, I can get it now. Thank you.
Oh, okay. So to complete the problem, let's go ahead and complete the problem. All right, equals. I'll try to show the work for this, but when we work out the Pythagorean, it's the square root of 1 minus x squared, I believe. But what do you want? You want, we're looking for cosine of u, right? Cosine is adjacent over hypotenuse. It's basically this guy. And you get 2x root 1 minus x squared. Right. 2x root 1 minus x squared. That's algebraic. And in fact, if you graph these on Desmos, and this might, again, shock you, but graph these on Desmos, right? Sine of 2 arcsine of x is this guy over here, right? What about 2x times the square root of 1 minus x squared? Hey, look at that. Same graph. These were equivalent expressions. Same graph. Y equals this and y equals that. Same graph. A good sign that they're equivalent. All right. Let's see. Okay, so why don't I do this? I'm going to start you on number 11, and then let me kind of zigzag through the students. So 10, you thought, oh, so 10, you're okay, right? 10, you're okay. 11, I'm going to start 11 for you, and see if you can kind of chew on this as I work with the others. So what's the deal with number 11? I'll start you off here. Whoops.
Wait, are you asking me?
Well, no, I'll go ahead and set you up.
Okay, thank you.
Yeah.
I just have no clue because I looked at the answer and I just had no clue where those, because I was trying to work backwards. I had no clue where the numbers.
Oh yeah, it's hard to work backwards. Oh yeah, it's a mess. It's hard to work backwards.
Because I just had no clue where to start, so I was just trying.
Oh yeah, see, when I show you how to start, then I think you may be able to crank it once I show you how to start. It's that first hurdle. It's that first hurdle that can get people. All right, let's go to green here. All right, so this is the 5-4-5-5 block. number 11. So this very first step might be enlightening, perhaps. So cosine to the fourth x. I don't have an identity for that. I do have a power reducing identity, a PRI, for this guy, cosine squared of x. How are these related? What can I do to cosine squared x to get cosine of the fourth x? How is this related to this?
Square it.
Correct. And for a lot of students, that's the key insight. I'll give you a second insight. Again, how can you expand this out? By using a PRI, a power reducing identity. Basically, take the power reducing identity, the right-hand side for this, plug it in, and then square that fraction. In the end, it may ultimately be an exercise in algebra, really an exercise in algebra, once you apply the PRI. So do you think that can help you get started and maybe see if you can chew on it? Of course, on Thursday, we can continue on with this.
Yeah, I can try to do it. And if I have a question on it, I can just save it till Thursday.
Sure. Yeah, I'd like you to give yourself a chance to try it out and
Yeah.
get your algebra right, because it's really easy to mess up the algebra. It's a good test of your algebra. No joke.
So then would you just square 1 plus cosine 2u over 2?
X. Yeah, 1 plus cosine 2x over 2.
Okay,
Right.
yeah.
Right. You're correct. And then it turns out that you have to apply the PRI a second time because you're going to get another cosine squared. You have to apply it a second time. That's why you end up with a 4x in there, right? You have a cosine of 4x.
Yeah.
Right. And again, now you're going to see this in calc too. Why is that? Because calculus hates powers like squares and fourth powers. So see, the thing is, calculus really loves this kind of form here. Number plus number times this plus number times that, because you don't have special powers on cosine. And a guy like this is really easy to differentiate or integrate term by term. And you do take derivatives and integrals term by term in calculus. So calculus loves this. Calculus, basically you have to take cosine of the fourth x and rewrite it like that, basically. All right, so try to work on that, and then if you have time later today, we can even go back to this. Let me try to go to some more students here. So I have a question on 646. Let's go to let's see. Let's go to, how about brownish? Brown. Okay, brown. Okay. 646. Oh, okay. Now, if you do 5, see, 6 comes from 5. If you do 5, you can get 6 from there. All right.
Okay, yeah, I was able to do 5,
Right.
and then it said where it says experiment and sketch some vectors. I guess I wasn't really sure about that because the way I was seeing it was they're the what do we call them? The magnitudes with the lines on the sides.
Yeah, they represent
They
length.
don't really have a direction, so I was like, how do I sketch a vector from these if they're not a vector and they're a scalar?
So here's the idea. We're assuming in the number 6, if V and W are non-zero orthogonal vectors. What's the more common term for orthogonal?
Okay, so perpendicular.
Yeah.
Okay, so I know that they're perpendicular, and then I just know. Okay, so one will be like vertical and one will be horizontal, and they'll
Right,
be
exactly.
different
So
magnitudes.
basically, you know what this is? This is Mr. Pythagoras. It's the Pythagorean theorem.
Hmm.
So see why this is the Pythagorean theorem. You're basically kind of labeling. Yeah. So can I do it here or? Yeah, I can do it right here, in fact. This length, if this is the vector V, this is the magnitude of V. If this is a vector W, the length is given by the magnitude of W. I gotta kind of squeeze it in here. Okay, and what's the vector V plus W? It's the resultant. It's the diagonal. Right? It's the resultant vector. And the length of this is
V plus W.
Okay. Now, okay, yeah. What is this vector? It's the vector v plus w, and the
Okay.
length is denoted by the length of v plus w. So what is this saying? The square of the hypotenuse, or the length of the hypotenuse, equals the sum of the squares on the other two sides. I should put
Got it. Yeah, I think I was just missing that piece with the connecting that the orthogonal meant that they were perpendicular, and that therefore that would give me my direction for the
right,
vector.
right. But it's really cool that, in a way, it's another way of approaching the Pythagorean theorem
Hmm.
more geometrically. Yeah. Okay. Very good. Very good. So that's 646. Any follow-ups on this? Any follow-ups? Going to 635C. 635C.
If I looked at the right one, that one should be pretty easy. You should be able to just take the answer from A and apply the magnitude to it.
Yeah. So so this is the vectors one. All right. So yeah. If you do A, right? Yeah. I think I think you're on the right track here. So if you do A, right? So you're finding the unit vector in the this is a quadrant 2 angle. So when you find the vector u, and how do you find the vector u? The vector u, you get it by normalizing v. It means that you divide it by its length. So you divide each component by the length. Okay, and then once you get A, you can do C, find the vector of magnitude 4 in the direction of V. You're correct. The answer is basically given by 4u. That's one of the purposes of normalizing, because then it's easy to construct vectors of whatever length, whatever specified length, just by multiplying the unit vector by the length, the desired length. And if you want in the opposite direction, you make it negative. Okay, so that's sort of the sketch. That
was Nick's question. So I mean,
Yeah, I got it now. Thank you. That's
You're
a
welcome,
lot.
yeah.
I was just looking in the wrong direction on it.
No, I understand, because I know on an exam, people often get confused by this. But again, that's a key purpose of normalizing a vector. Why do we want this stupid u vector, right? Well, for one thing, it's used in calculus 3 proofs, but also, as we've said, it's like a penny, right? You can build anything off a penny, right? So here we take u, and then we want a vector of magnitude 4, multiply it by 4. And you're guaranteed that the result will have length 4. And it's pointing in the appropriate direction. Very good. Okay. Let's see. And we had 1 and 3 on the same section, I presume. 6-3. Okay. Sort of chatting with a student here. I'm not sure if 1 and 3 were. I'm not sure what section the 1 and 3 are referring to. I'm trying to get some clarification. So as I wait for clarification on which section, okay, I see here 8A and C on the 5-4-5-5 block. Oh, I see. Yeah, that's right. That's right. Okay, yeah, it was a quadrant question. Okay, so we're going to go to 5-4-5-5 8AC. All right. And thank you for answering that question, by the way. Okay. Up. Right. So 8A, that's verifying the kind of stunt we pulled back in chapter 4. All right. So in fact, 8A, I'll set that up with maybe a line or two. I think you'll have fun getting it. So let's start that off. Okay. And then try to see if you can complete it. So this is whoops. Okay. All right. So here in brown, Let's look at 8a. Let's start to set up 8a. Okay, but I think you'll have fun just kind of working it. All right, so sine of theta plus pi. All right. Oh, this is a 5455. A. Let's start this off. All right. So sine of theta plus pi. Well, if you apply the sum identities for sine, all right, it's the sum of the mixed up products. I might run out of room, so I'm going to do it on the next line here. I might run out of room. Sum of the mixed up products. So it's going to be sine of theta cosine of pi plus cosine of theta sine of pi. All right. So you know what? Go ahead and copy that line. I'm going to go ahead and leave the rest to you. What is cosine of pi? What is sine of pi? And you're already very close. All right. So I'll leave the remainder to you. Once you get this, you should be in good shape. Look at the unit circle. I can come back to this. Let me go to 8c. 8c. Yeah. It's great when you see the solution, but many great students ask for this one. Yes. All right. So let's do it a different color. How about blue? All right. C. The 5455 block, 8C. All right. So we're going to express tangent in terms of sine and cosine and show why this is true. Okay, based on the sine and cosine sum identities. All right. Let's go to blue. Tangent of u plus v. By the quotient identities, what's that equal to? By the quotient identities. That's going to be sine of u plus v over cosine of u plus v. All right. And then you're going to write out the sum identities for both. Sine of u plus v, again, sum of the mixed up products like up here. Sine of u, cosine of v plus cosine of u, sine of v. It's a good habit to have this term first because if you ever need a difference identity, it's helpful to have this term first. Cosine of u plus v, that's the cosines minus the sines. Cosine of u, cosine of v, minus sine of u, sine of v. All right. Aim for the target. But you know what? I'm going to look at this lowly 1 over here. I want the bottom left to be a 1. So what can I do to make the bottom left equal to 1? Well, I can divide this by itself. But I can't just do it because I feel like it, right? I have to divide every term on top and every term on bottom by this. So I'm going to do, okay, so I'm going to start this off. In the upper left, you're going to get sine, oops, sine of u cosine of v all over cosine of u cosine of v. And you're going to do the same for this, this. We know this guy divided by himself is 1. So you just put a 1 there. All right. But that's the strategy. And you're going to get some great simplifications when you look at the upper left, upper right, bottom right. And then the 1 should be straightforward because cosine of u cosine of v divided by himself is 1. But that's the idea. You want to divide the two terms on top, the two terms on the bottom, by this magical guy over here. Why? Because we want a 1 in the bottom left. That's a matter of strategy. All right. So 5.49a. All right.
Yeah, so for 9/8, I got I got the pi over 12 is one of the parts of the solution set, but I don't know how to get the other 3.
Well, we should start at the beginning. Let's see if we can sort of trace your steps through this. All right, 9a. All right. So let's check to see if, let me, 5.4, 5.5, this is number 9a. All right. So let's check yourself so far. So you start the given equation, all right? And you notice, hey, if I factor out a 2, right? So 2 times sine of x cosine of x minus 1 equals 0. We can add 1 to both sides anyway, right? 2, what's 2 sine of x cosine of x? That is
Sine 2u or 2x.
sine of 2x, right? So we have now 2 sine of 2x equals 1. All right. Once again, I think substitution can be your friend. Well, I mean, we can do this step, divide by 2. We can do that.
Yeah, that's what I did.
That's fine. And then do a substitution. Let u equal 2x. All right, because we don't want to go backwards, right? So we're going to do a substitution. All right, so we have sine of u equals 1/2. Think in terms of u. Think in terms of u. Oh, I'll do this in purple. Okay, in terms of u. In what two quadrants is sine positive? In what two quadrants is sine positive? Like positive
1 and 2.
1 and 2. Low guy here. His brother over here. All right. In fact, there's a famous angle whose sine value is 1/2. It's the low guy. Sine of 30 degrees, or how many radians? Pi over 6. And then who's his famous brother in quadrant 2?
5 pi over 6.
5 pi over 6, right. Okay. And those will be helpful as we construct a general solution for u and then x. All right. So for right now, all right, u could be pi over 6 plus 2 pi n, all the coterminal twins, or u could be 5 pi over 6 plus 2 pi n, where n is integer. I'm going to need that at some point. All right. So u was 2x. I just do this. U was 2x. So in both cases, we want to divide by 2. If you divide by 2, you're multiplying by what number? If you divide by 2, you're multiplying by
1/2.
1/2. Correct. Okay. Any questions so far? I know that you're asking me to kind of verify some answers, but I couldn't do that out of context. Any questions? All right.
I wasn't substituting in the u. I was just doing sine of 2x equals 1/2 and then taking the sine inverse and then dividing by 2. So I only
Ooh.
got pi over 6.
Yeah, that's the thing, though. I mean, you got to be careful. You got to be very careful about how you use inverse sine and so forth. You want to make sure that you're getting all relevant pieces, right? You agree that so far I'm getting all relevant pieces, at least for you.
Yeah.
Right. Okay.
Uh-huh.
But wait. U was 2x. Okay. I remember before I forgot to sub back. Remember to sub back, right? And you agree that you don't have to completely rewrite these if you know, hey, these are both 2x. In both these equations, we have to divide by 2x on both sides, or in other words, multiply by half. All right. So on the left, we have, after we divide by 2, x equals, and then here, it might be helpful to think, if you divide by 2, you're multiplying by 1/2. 1/2 times pi over 6 plus 1/2 times 2 pi n for the first block. Or x equals da da da. What, 5 pi over, it's going to be 5 pi over 12. But it's going to be a 1/2 times 5 pi over 6, plus again the pi n. This is basically pi n. And in the end, we're going to need, for the general solution, as an integer. All right. What's half of pi over 6? 1/2 times pi over 6, pi over 12, plus pi n. So the solution set will consist of the set of all x's in the reals, such that we have this piece here, x equals pi over 12 plus pi n, or with n integer, coming from over here, we have x equals half of 5 pi over 6 is 5 pi over 12. Still plus pi n. All right. And that's going to be the general solution set. So do you agree that's a general solution set? Do you have any questions about the work leading up to that?
No, I don't. But where do you get the 13 pi over 12 and the 17 pi over 12?
Oh gosh, I could have answered that so simply for you. You add pi. Because pi is the increment. Pi's right. So
okay.
Yeah, we're lucky. We're lucky because this goes fast, right? Because there weren't that many. But the idea is, so we can do so here's the idea, like in the notes, right?
Yeah, well, it's just if n is 1, then both of those
Right.
equal.
So this
I see.
right. Pi over 12 corresponds to n equals 0. You don't want to go backwards, because if you subtract pi, you're going to get negative angles. And I'm focusing on angles between 0 and 2 pi, right? In part B or whatever, right? But then you want to add pi. When you add pi, that means that you're adding 12 pi over 12. It's very similar to the frame method problems we did back in chapter 4, right? When you add pi, you're adding 12 pi over 12. 1 pi over 12 plus 12 pi over 12 is 13 pi over 12.
Yeah, okay. I got it now.
Right. And then similarly over here. So there are 4 solutions. Okay. Bear in mind, I don't feel I was wasting the class's time. I'm sure a lot of people had questions about how to get to there in the first place. So, okay. So I feel that this was time well spent in any case. Ideally, you want the solutions in solution set form. On an exam, I would have accepted just boxing in like that. But if you have time, try to put it in between the braces so you have a nice solution set form. Okay, so we did, yeah, we went over 9A, right? 6.3C. Okay, and I'm saving these. I can refer back to these if you need them, or if I need them. Okay, 6.3C. I guess 1C, yeah. Which 6.3 1C? Is it 1C? Section 6.3, which C?
3C.
Sorry?
6.3, 3C.
3C. Thank
Oh,
you.
E. I mean 3E. should say.
6.33C. Okay. That's probably my fault because it'd be convenient if it were number 1, number 2, but I want to give you smart homework assignments. Okay. 6.33C.
Oh, 3E. Yeah. 6.33E.
Oh, E.
Yeah.
Okay. Right, because C was pictures.
I think
Oh.
that one is completely unrelated to what I was doing. I get A and B and C, D, but when I come to E, I look at your answer and I see different.
Okay, 6.33E. Okay, so I think I can do this in text. All right. So 3W minus 4V. Now you're supposed to, put the little arrowhead things on top. Let's not worry about that right now. Well, I'll do it once. 3. W. All this mess for an arrowhead. Okay, I'll do it once. There we go. Okay, 3W minus 4V. All right. 3 times. W was 3 comma 1. All right. And then minus 4 times 1 comma 2 in angle brackets. All right. Okay. Now, let's see. They're hiding over here. Okay. Equals. Now, basically, the scalar multipliers distribute. So 3 times 3 is 9. 3 times 1 is 3. Okay, so 3 times that first vector, 3 times the W vector, is angle brackets 9 comma 3 in component form. Now here, like I keep saying, it's easier for people to add and subtract. Although here, it's not so bad, actually. Minus 4 times 1 is 4. 4 times 2 is 8. All right. To subtract vectors, you subtract corresponding components. And we should be done. 9 minus 4 is 5. 3 minus 8 is -5. Although I wouldn't put myself past messing up some arithmetic. 5 -5. Thank you. Yes, I'm relieved. The angle 5 comma -5. So do you see the discrepancy?
I messed up when I was with the numbers. That's why I couldn't do it.
I see.
I didn't know you were gonna distribute that one. That's the way I messed up.
So in a way, they do distribute. Yeah.
Yeah.
Right.
Thank you.
You're welcome. Yes. Let's see. Yes, thank you all for your perseverance. We're at 10:17. I can take a few more. Where are we in chat? Let me see here. Oh, I think was that all in chat? Well, it's 10:17. Thank you all for your perseverance. Was there anything else? And of course, we will have the full day on Thursday, by the way, and I should be able to stick around after class Thursday. Sometimes I have to do something at 10, but I can stay a bit after class at least. Thank you. Yes. Was there anything else? Any other questions? Any other questions? Thank you. Thank you. So at this time, let me come back at 10:21 and see if there are any last minute questions. I'll pause for now. Pause/record. Okay. So I'll pause for now. I'll come back at 10:21 if anyone has any.